Welcome to the second part of this lecture, which is on Boolean algebra. So in Boolean algebra, we present an algebra which deals with binary variables and logic operations. And the variables in this are generally denoted by letters of the alphabet, and they use the binary operators, which are or, and not. The Boolean algebra laws, which are listed below, were formalized by the English mathematician George Boole in 1954. These basic identities and laws include the existence of 0 and 1, which is these first four, where x or 0 is x or 1 is 1, x and 1 is the same as x and 0 will never happen, so it's 0. And then these other laws are idempotence, where x or x is the same as x and x is the same as x or not x is basically covering all cases, so it's 1, and x and not x can never happen, so it's 0, and this is called the existence of a complement. Then involution is that if you double negate it, so x not is the same as x. Boolean algebra also follows the commutative laws, where it doesn't matter which order they're placed in, x or y is the same as y or x, and the same as x and y is the same as y and x, although generally we would write it in the order in which the letters fall in the alphabet for consistency. Boolean algebra also follows the associative laws, where you can group using parentheses, and as long as you don't change the operation, then the meaning is the same. So x or y, all ORed with z, is the same as x or y or z. And in the same way, in parentheses, x and y, and z is the same as x anded with parentheses y and z. They also follow the distributive laws, where you can expand brackets. So x outside of the brackets, y or z, is the same as x and y or x and z. And this other one, which is interesting, which we'll prove later, which is that x or y and z is the same as x or y and x or z. Then follows the De Morgan's law, where the complement of x or y is the same as not x and not y, and the complement of x and y is the same as not x or not y. And we will also prove that one later. In terms of the properties and the algebra, we have something called dual and self-dual, and the dual of an algebraic expression is obtained by interchanging the ors and the ands, that is, interchanging the plus operator and the dot operator, and interchanging the zeros and the ones, where identities appear in dual pairs, and when there's only one identity on the line, the identity is called self-dual. That means that the dual expression is equal to the original expression, which is not necessarily the case, only in the self-dual case. Something else for going forward is, if it's unambiguous, we often leave out the dot operator, although we never leave out the or plus operator. And so, as I said before, unless it happens to be self-dual, then the dual of the expression itself does not equal the expression itself. So let's look at these examples. We have f equaling to a or not c, and b or 0. And the dual of f is we exchange everywhere where there was a plus, then we change it to a dot. So everywhere there was an or, we change it to an and. Everywhere there was an and, we change it to an or, and everywhere there was a 0, we change it to a 1. So in this case, the dual of f is a and not c or b. So let's do another example here. We've got an x, we change the dot and for a or. Y, we have an or operator, so we change it to an and operator. W and z. And since this is all grouped together, we have to have the brackets like this. And then for this second expression, due to De Morgan's theorem, we can change it. Instead of the complement of w and z, we have x or y and w or z. We have x or y and, in brackets, not w or not z. So for this one, once again, swapping the signs, and then we have from the distributive law that A or B and A or C is the same as A or B and C. And then we leave this last expression as is, and then we can expand that out, and then we get rid of these double terms, and we have AB or AC or BC or BC, which is the same. So equals AB plus AC plus BC, which is the same as that original expression. So therefore, we can say that this last one, H, the dual of H, is the same as H, therefore it is self-dual. So only function that's self-dual is this third one. In terms of the Boolean operating procedure, then it is parentheses first. That is, these parentheses are the first thing that you evaluate, and then the not operator on top of this D, then and then or. So the consequence of this is that parentheses must appear around or expressions in order to group them properly. So let's do another example. This one's an algebraic proof of the absorption theorem. We want to prove that A or A and B is the same as A. So we can call A here A and 1. This is since X is the same as X and 1. This is the same as xy or xz equals to x outside of y or z, distributive, and then a equals to 1 since x or 1 equals to 1, which equals a since x and 1 equals to x. So there is it written more formally. And so the reason we do proofs is so that we can learn how to be careful and efficient with the use of the identities and theorems in Boolean algebra, and how to choose the appropriate identity or theorem to apply to make forward progress, whatever the application is. So here's another example. This one is to prove the consensus theorem. AB or not A and C, or B and C is the same as A and B or not A and C. So here we have to also write the justification. So how did we get from BC being the same as 1 or BC, since X is the same as 1 and X, and this one since X or not X equals to 1, the existence of complement. We can expand this out and then continue to manipulate the Boolean algebra, writing our reasoning on the right hand side until we get to the final answer. So here's the third example, a Boolean algebra proof. So we've got to prove that the complement of x or y and z, or x and not y, is the same as not y and x or z. So we start with the left-hand side. We use De Morgan's theorem, and then we use the commutative law, and then the distributive law to group it further, and then the distributive law to group it even further again, convert not x or x into 1, then use the commutative law one last time so that we can rearrange x or z, so that equals the right-hand side. And here it is written again a little bit more neatly. So here are some useful theorems that you should be aware of, and they are the minimization theorem, the absorption theorem, simplification theorem, consensus theorem, and De Morgan's theorem, which we already mentioned before. So we've already proved the absorption theorem and the consensus theorem. So here's the proof for the minimization theorem, this one at the top here. First of all, proving that x and y, or not x and y, is the same as y. So we can say this is equal to y outside of x or not x, which is the same as y by 1, which is the same as y. And this one, we can say this is the same as y or x and not x because of this distributive law. This is the same as y or 0, since a and not a is equal to 0, which is the same as y. So great, we got to the right-hand side for both minimization cases. And that was the two of them being proved separately. But something else that's interesting is that x, y, or not x, that if f is this, the dual of f equals. And so you could also say that the second expression holds by the duality of the first expression. Another way to prove the second expression without using the distributive law is to expand it out first. Since a and not a equals 0 and a equals a, this is equal to the following. Since a or not a equals 1, y or y equals to y equals the right hand side. Since a and 1 equals 1, a and a equals a. So for here we have the Boolean function evaluation, and we have 4 functions, 2 of which already filled out inside the truth table, the other 2 which we need to fill out. So let's just confirm those first 2. So for the first one, it's only true where x, y, and not z. So x is here, y is here, and not z is here. So that's right. For F2, it's where x is true, so therefore anywhere here, and also or where y is not true, so that is up here, and where z is true, so here. So there you go, we've got all of these ones being 1, and then also this one here. So for F3, we have these 2 terms that use all x, y, and z. So let's follow that through. We have not x, so it could be any of these, and not y, so it could be any of these, and not z, so it can only be this one, so we put a 1 here. And we also have not x, so any of these, and y, so any of these, and z, so here we put another 1 here. And also when x is true and y is false, so that is x is true and y is false, so both of these get 1s in them. And then for all the others, we put 0s in those rows. And we'll check our answer. That's good. And then F4, we have F4 being true when x is true and y is not true. So that is, once again, these ones here. So we'll write 1s here in those rows. And when x is false, so could be any of these 4, and when z is true, so it could be either this on this one, so here and here, and then we write 0s in all the others. And we'll check our answer, and good. So in this case, we're going to be using Boolean algebra to do simplification, and when we simplify, we're trying to reduce the number of literals, where literals are these letters A, B, C, D, D. We can count how many there are, and we want to reduce that down to the smallest possible number. So we can notice that this not A, C, and D, similar to this not A, C, and not D, so we can write those together, take out the not A and C, and also that this A, B is also in here, so we can do or A, B, or C, D, and then finally write this one out. And then we can notice that D or not D is the same as 1, so this is not AC, and 1 or CD is the same as 1. Then we can notice that there's a B here and a B here, so we take the B outside, B, A, or not A, D, or not AC. And if we have A or not A and D, then there's no need for this not A, because it's already covered by the fact that we've got A here, so A or not A, D is the same as A or D, so this is B outside of A or D or not AC, and that's the best we can probably do. And this is 5 literals, 1, 2, 3, 4, 5. And here it is written again a little bit more neatly. In order to complement a function, we use De Morgan's theorem to complement the function, and we take these 2 steps. First of all, we interchange the and the or operators, that is, the dot and the plus operators, and then we complement each constant value and literal. So let's show this with an example. First of all, we have f being the function equaling to this, so the complement of f is equal to, we will replace each of the ands with ors, and we will also complement each constant value. So the not x becomes x, the dot in between here and here becomes plus, this y becomes not y, this dot becomes plus, put this in brackets, this plus becomes a dot, another bracket, the x becomes not x, the dot in between, plus y not becomes y, and z not becomes z. So let's do another one. Complement of G, write it with a bar over the top, equal to, we can scribble all over this actually. We will put bar here, a dot here, bar here, plus in between here, bar here, plus here, bar here, a dot here, and a bar here. And then we say that is A, because two knots become negated, B knot or C knot, then written without the dot and the parentheses, and finally written a bit more cleanly. All right, so that's good. We got that right. And that's the end of this part. And I'll be seeing you in the next one for a lecture that talks about the canonical and standard form.